Hi there, folks. I hope you're all doing well. Professor O'Hara here, and I'd like to do some 1600 style questions for you. So I went digging through my files really far back to some 2010 quizzes. Okay, some quizzes that we put out way back when in 2010. We were still running this course, but it's almost a decade ago. I don't think you can find these up online, but I've got them from my personal file, so I want to go through a few of them. And the reason I want to go through these quizzes and make these videos is to sort of, well, make up for the fact that this course is kind of dense. Okay? We tend to sort of just truck along theory after theory after theory. You know, we do examples here, we talk about what these things mean when we can, but I feel like most of the questions are done sort of in lab or in your homework, and I just want to showcase more the style that we look for when it comes to actually doing computations, and discuss how I work through a question and maybe how you might start working through a question if you get stuck. Of particular note, I want to pay attention to these theory style, true or false, is it true that this happens, can you think of a case where this doesn't happen questions. Because we're going to see a few of those on the midterm. At least that's the way our most recent draft looked. If that changes, so be it. It's more of a calculation midterm. But the reason I want to focus on those is because you tend not to get a lot of those when you do Maple TA. Okay? Maple TA is very hard at marking explanations and justifications. But way back when, in the before time, in the long ago that was 2010, we had a small enough class size that we could get TAs to give out the quizzes and mark them. And so we could ask theory questions. And since the midterm looks like it's going to have some theory questions, these ones I want to pay particular attention to. I'm still going to do the calculation questions, but you guys have had lots of practice doing calculation with your problem sets and your quizzes in Maple TA. And so, I think it all balances out. But how exactly do we think through a theory question? Well, how do we think through a true-false question? Well, we're going to find out. Okay? Now, fair warning, I want to say this up front right away. I'm going through a selection of old quizzes. Is this going to cover every nook and cranny of the course? No. So you have been warned. Okay? You still have to study. You can't just watch these videos and get off scot-free. This is more of a how do we think through questions than it is review. Okay? Am I going to try and, get a nice spread of questions? Absolutely. But sometimes I just don't have a quiz where a particular concept was explored. Just because you don't see me go through an invertible matrix question or something like that doesn't mean it's not on the test. If it's in the chapter of the textbook that we covered, if we mentioned it in class, or you saw a similar question on a problem set, that's fair game. Okay? Doesn't mean I'm going to do a video about that particular style of question. But I'm going to try and be fair. I'm going to try and cover as many things as I can as I post these videos throughout reading week. But you can't come to me after the exam and say, you didn't do a linear independence question on the quizzes. I was tricked. No, you've been warned. Okay, you still have to study everything. But with that said, let's dive into a few questions and just talk our way through these questions and, maybe review some of the littler results that we didn't quite remember from the start of the course. Okay, so what have I got here after that lengthy preamble? Well, I've got the first quiz from section 4 from 2010. So it's a long time ago. Long time ago. But we've got, I think it's just 2 questions on this one. Yeah, 2 questions, okay. And this first question here, what have we got? We got U, V, and W, they're vectors in Rn, so it's nothing particular like R2 or R3. And we're just asking 2 theory questions here. Is it true that if U is orthogonal to V, so we might try and remember, what does orthogonal mean? It's perpendicular. So if U is orthogonal to V and W, then U is orthogonal to V minus W. What does orthogonal mean? Well, if I know U is orthogonal to V, then when I dot product it, I get 0. Not the 0 vector, the scalar 0. Same thing with U dot W. It's also equal to 0. But what would I like? Well, they're asking me, does this mean that U is orthogonal to V dot W? Well, if I think it is, then I should be able to take this expression and do a whole bunch of equals and equals and equals and get down to a 0. If I think something isn't true, okay, maybe it's a true or false question. If I think something isn't true, a good idea to showing that it's false would be to think of a vector u and a vector v and a vector w that satisfies the initial conditions. The stuff that they're telling me, if this, so think of some u, v, and w that satisfy the this part. So they say, if this, then that. So find me things that satisfy the this, but still don't make the that part true. This is how we show something's false. And depending on whether or not a question actually asks you to justify it, you might have to write down some of your reasoning. But if you think something's false, try in your head to find a situation where the initial conditions are satisfied, but you don't get the same end result. That's how you can really tell if something's false. Okay? Gut reaction only goes so far. Sometimes you just think, it can't possibly work out. And sometimes you're right, you make that guess, and you circle false, and something like that, and you're right. But sometimes when you say, I just don't think it'll work, somebody comes along and says, no, you forgot theorem 3.13, and no, it's absolutely true. There's two ways to attack a true-false question. You try and show it by assuming the initial conditions, the this part of if this then that, and try and prove the that. You try and just show, equals, 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 implies, 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 and get the that. Or you try and show that there are some vectors that satisfy the this, but don't satisfy the that. Okay? So, getting back to our question, I think this one is true. Now, if I wanted to, if I was, sort of on the fence, I might just say, well, can I find a u that's orthogonal to two other vectors, v and w? And then, then compute v minus w and see, does this really work? But I remember one of our results from a long time ago that says, well, u dot, if you got a sum or a difference, it distributes. Okay, and I don't even need all these equal signs. I'm going to get there actually fairly quickly. Because what did we assume? We assumed u dot v was 0. And we assumed u dot w was 0. So this is 0, but that's exactly what it means to be orthogonal. It means perpendicular. It means you're going to get a right angle. So this is true. Fantastic. Okay, what's going on in B? Is it true that if u plus v equals 0, this time it'll be the 0 vector. You can tell because it's bold, or, if maybe it has a hat on it. But more than that, when I add two vectors, I should get a vector out. Okay? So is it true that if u plus v is 0, then u and v are vectors of the same length? Okay. So immediately when I see that, my mind starts racing. Okay, length. I should probably talk about length. Should probably use those the double absolute values, as some people call them. And I should maybe start trying to remember, okay, how do you calculate length? Do I remember any results that involve length? Okay, those are the sorts of connections we need to start making. Okay. Now, one thing you don't want to do is say, well, this one was true, so this one must be false. It's never how it works. In fact, I know specifically there are some teachers out there who have given out an all-true exam. And, some students will just put false because they feel false has to be somewhere. No. We can make every question false. You can make every question true. It's about whether or not people can make the theory connections. Okay. So, well, if u plus v is 0, this isn't the greatest thing to work with, because if I want to start doing lengths, well, this isn't exactly going to help, and it's not going to talk about u and v's lengths. Okay? Yeah, we have the Cauchy-Schwarz inequality, which might help out, but that's an inequality. Okay, what else could we do? Well, u plus v equals 0 is really just a fancy way of saying u is negative v. Now I've got u and v separated, I could talk about their lengths. So I can do the length thing. As soon as I apply a length to one side, I apply it to the other side. Well, there's the length of u right there. Great. This isn't quite the length of v. But we had a result from class that said if you scalar multiply, then the scalar multiple can come out at the cost of an absolute value sign. Well, what have we got? We've got negative v. That's negative 1 times v. So at the cost of an absolute value sign, you get absolute value of negative 1 times the length of v. There's the length of v. And the absolute value of negative 1 is just 1. So the length of u is equal to the length of v. Hey, it's true. Okay. So that's our first question there. A little bit of true, false, a little bit of theory. Okay. You'll notice there were no numbers whatsoever in the question. There was nothing I could do to calculate it. It was all, do I understand these definitions? Do I know what orthogonal means? Do I know what a unit vector is? Unit vectors didn't come up, but that's another example of something small. Do I know how to calculate directions? Those sorts of things. Do I know theory about how to calculate or theory about how to work with angles between vectors? Okay. So that was question 1. Onward to question 2, our second question on this little quiz from 8 years ago. Okay, so we've got n. It's bolded, so that tells me it's a vector, and immediately I start thinking that this should be a normal for a plane. And as I read on, I find that's true. Find a general equation of the plane that passes through 0, 1, negative 1, and has a normal of n. Okay, so we've got sort of imagine our plane. It passes through this point here, 0, 1, negative 1. And the normal vector just sort of sits orthogonal. Okay, just sort of sits orthogonal out there. Perpendicular to the whole plane. Okay. So this would make a great A part for sort of a longer question about, planes and maybe distances from points to planes or intersections of lines and planes. These are fantastic things. And we usually try and break them down on questions. So find a general equation. So general equations for planes in R3 look like this. But the A, B, and C form the components of our normal vector. So I know that this is actually going to look like 1 times x minus 2 times y plus 3 times z is equal to d. But what's the d here? And that's where knowing the point on the plane comes in. Because if I just give you a normal, well, you can get me a whole bunch of planes. They're all going to be parallel to one another. But only one of them will happen to pass through the given point. So it's going to have to satisfy this equation. So 1 times 0 minus 2 times 1 plus 3 times negative 1 is going to be 0 minus 2 minus 3, negative 5. So d is negative 5. And our general equation is going to be x. We usually don't write the 1. X minus 2y plus 3z is negative 5. And there we go. And if I were doing this calculation, I'd probably put a little box around it to really highlight to whoever's marking that this is my final answer. Okay? We'll sort of erase part of the bottom of the box because I do want to read the next part of the question. Write a parametric form of the line through the origin in the direction of n. Okay. Now, they're being a little sneaky here. Just a little sneaky. Usually, when we say, give me a line, and they say in the direction of, that's a direction vector. We have to cast our minds back a little bit, a little bit of 1.3. But we do have lines, they do have direction vectors. When you're in R3, that's really sort of the only way to go. But where's the point? Where's the point that we need? Because you always need a point and a direction. Okay? Point and a direction, whether it be parametric or vector form or anything like that. Where's the point? I don't see any numbers. They're just being a little sneaky, and a lot of people will, ignore this because they'll have caught this, but through the origin means that I pass through 0, 0, 0. Why 0, 0, 0? Well, from the earlier parts of the question, I'm clearly working in R3 because I keep seeing 3 coordinates, 3 components. So it should be 0, 0, 0. Not 0, 0, not 0, 0, 0, 0, 0, 0. Just 3 zeros. Okay, so parametric form. That's the one that looks like x equals, y equals, z equals. If you had more, you'd say x1, x2, x3, x4, x5. And then it has a parameter t. So we usually write the value, the coordinates for our points, and then plus, and then t for our parameter. Now t can be any real number. And then we need our direction vector. Well, they happen to give us our direction vector at the start, 1, -1, 3. So now we multiply t by the components of our direction vector, 1, -1, and 3. And we can simplify this a little bit. No one really writes 0 plus, so we might just say instead x is 1 times t is just t, y is -2t, and z is 3t. Now, I know these questions are sort of basic, lines, planes, old stuff, basic stuff, really. But, we can start making some other connections in our head. We could ask more complicated questions of ourselves. For example, this line here has a direction vector n. It's going to hit at what angle? Little thought experiment. What angle of the is it going to make with the plane in the previous question? Should be perpendicular. Why? Because its direction vector is n, so it's going to stick up right through that plane. Or other things we could, maybe note as we make connections in our head. This line here passes through the origin. What did we learn in class oh so recently? Lines and planes and hyperplanes and k-dimensional spaces, as long as they pass through the origin, they're going to be subspaces. So this is a line, but it's also a one-dimensional subspace, and I could give you a basis. Okay, it would be 1, -3, 3. Okay. Now, I'm not going to make connections every single time I talk about one of these quizzes, but we've done one of them. It's got some good questions, some theory about lengths and orthogonality, and it's just got some good old computation that we're comfortable with. Get me this plane, find me this line. Okay, we might see some intersections or something like that on the next quiz. Who knows? Okay, but if you're interested in these sorts of things, if you like hearing the thought process behind them, stay tuned, and I'll be adding some more quizzes to this playlist, really whenever I get a chance. Life of a prof, kind of busy, but here's one, and here's hoping that I'll have a few more in the future. Okay? Have yourselves a wonderful day. I'll see you next time.